Okay, let's take a look at example 7 next. All right, so the instructions here are to use the change of variables formula, which we conveniently got right above, to compute the following integral. All right, so we've got the double integral over a domain D. D is given to us in the figure on the right, and it says compare with example 5. So the function we're integrating x squared plus y squared is not a challenging function. So really what makes this example difficult is the domain. So it's curvy and it's interesting here. And if you think about it, you have to actually split this up into three pieces, okay? Where, again, if you draw this with Desmos or some sort of more accurate picture, this is kind of hand-drawn. It maybe looks like you can do it in two different pieces, but really you actually have to split it up into three, where you've got top, bottom, top, bottom, top, bottom, and again, they kind of, all of them are slightly different, which is why we need three pieces. If we were to do this just using type 1 integrals that we introduced earlier. Okay, so the idea here is the change of variables formula allows us to change variables and write just a single integral here. Now, this is essentially a continuation of the example 5 that we already did. So I grabbed a couple of the key information from that example where we introduce this transformation t that sends points in the uv plane into the xy plane, and the transformation is x, the x coordinate is u divided by v, the y coordinate is u times v. Okay, and remember in that example we learned that if I send the u variables from 1 to 2, u equals 1, u equals 2 would be these vertical lines here. These lines get sent over to, I can't remember, let's see, I think it was the hyperbolas. And then the v equals 1 and v equals 2 get sent to the straight lines over here. Okay, and we actually got the 4s because the formulas had a u squared and a v squared. Okay, so we also calculated the Jacobian in that example, and we got that the Jacobian of t was 2u divided by v. Keep in mind, u and v are both positive for the domain of integration here, so I don't need absolute values. Okay, so cool. I think we've got all of our ingredients, so we should make quick work of this calculation. So let's see what we have to do. Okay, so this is the integral we'd like to calculate. The change of variables formula tells us that we can write this as a double integral over d star. Okay, and just take a quick peek at that formula up there. D star Okay, we do need to change x and y into the new variables u and v, so let's go ahead and do that right now. Since we know that x is u divided by v, I'll put that for my x squared plus v squared. I'm sorry, y squared. Y squared is u times v. All right, so that is my function expressed in the new variables. Next up, we remember we have to do the Jacobian, so let's multiply that by 2u divided by v. And finally, we have the new variables. We got du, dv, which we always take a minute to think, do we care about the order? So to answer that, we look at the domain of integration. Since d star is a box, well, I can write these in any order, okay, since we've got constant limits of integration by Fubini's theorem. Cool. All right, so that is the new integral. Nice. Let's go ahead and set this up. So both of these are from 1 to 2. 1 to 2. Okay, let's simplify this. So let's write this as u squared over v squared plus u squared v squared. Then I'm going to need to distribute this 2u divided by v. du dv, again, I don't really care about the order since now that everything is expressed, it's over a rectangle. Okay, let's distribute and just calmly take care of the algebra. Don't need to do the color coding. Let's just, okay, 1 to 2, 1 to 2. All right, so let's see. This times 2u over v, I've got 2u cubed divided by v cubed, and plus, let's see, 2u cubed times v, so looking at this, before we start evaluating, so we can certainly do this as an iterated integral, but take a quick peek at this, right? Notice that I really just have u cubed in both pieces. So I'm going to use the sometimes useful trick. So to split this up as a product of integrals, 1 to 2, u cubed du times 1 to 2, all the other stuff that has the v. And in fact, actually, since both of them have a 2, let me make my life even easier and take the 2's out. I'll be left with v to the negative 3 plus v. Okay, keeping in mind I'm thinking of power rule in my next step. Okay. So let's integrate. 2 times the integral of u cubed is 1/4 u to the 4th. U goes from 1 to 2 times, let's see, power rule, v to the negative 3, add 1 to the exponent. That's going to be v to the negative 2 divided by negative 2. Let's write that as negative 1/2, 1 over v squared. Okay, let me put a parentheses here since these are going to be 2 pieces. And then, okay, integrate v, 1/2 v squared. This goes from v goes from 1 to 2. All right, let's continue. So 2 times, plug in u equals 2. So I've got, what is that? 2 times 2 is 4, and then 4 times 4, we've got 16, divided by 4, and then we've got minus 1 divided by 4, so let's write it this way. Okay, what about plugging in v equals 2? So we're going to get, so 2 squared is 4, 4 times 2 is 8, negative 1/8, plus v squared, so that's 2 squared, that's 4. 4 divided by 2 is 2. Okay, let me do some extra parentheses here so that we can not fumble the football here as we simplify. Okay, now let's plug in 1. I'll get negative 1/2 plus 1/2. Sweet. Okay, this is 0. Almost done. So the 2's going to cancel with the 4, leaving me a 2. 16 minus 1 is 15, so I've got 15 divided by 2. All I have left to do is to do 2 minus 1/8. What is that? I guess multiply 2 by 8 divided by 8, giving me 16. So I've got 15 over 8. And one more step, we've got 15 squared divided by 16. Pretty satisfying looking answer here. And let's take a look at the beginning of the problem. So all we had to do is just compute this double integral, and we've done it. No story with the problem, so there is our answer, 15 squared divided by 16. Lovely. Okay, another problem. So this time our task is to compute the following double integral. We've got the double integral over a domain D of the function x squared minus y squared times d8. Okay, so pretty easy function to integrate. So the trick is, what is the domain? Well, the domain is a parallelogram with vertices plus or minus 1 comma 0 and 0 plus or minus 1. Okay, and then I've got a question here. Is it surprising? Why or why not? Let's think about that once we've got our answer. Okay, so let's start by drawing the domain D. So this is going to be in the xy plane. All right, and I want to draw this nicely, so let's see. Let's do 2 markings on the left and on the right. That will be 1 and minus 1. Do a better job with my y-axis here. Okay, better. Here's 1 and minus 1. Okay. So I've got these 4 points, and it said it's the parallelogram with these 4 points as vertices. So we've got the following rotated square. Okay, and this is going to be the domain D. So we certainly could cut this up into different chunks and then evaluate this as a type 1 integral. It's not too difficult. We're going to have to do some of the work that we're going to do in this example anyways, but of course, the idea is maybe if we can come up with the right transformation, we can use the change of variables formula to rewrite this as a UV integral, and it makes it easier to calculate. Okay, so the key is, can we find the transformation t or t inverse? So it depends on which order, so that we can integrate. So let's give this a try. Okay, and let's think about how we might go about doing this. Again, this time there are no transformations given to us. We have to come up with them on our own, okay? And right now there's really nothing to look at. So what we should pretty much do is, why don't we just start coming up with the equations for these lines? Okay, so these will be pretty easy to do. Again, we're starting off in the xy plane. So as long as we are looking at the right point, we can just use point slope formula for all of these. Okay, so y is equal to, so the y-intercept is 1. What's the slope? Okay, we're just going down 1, so the slope is -1. Okay, there's our first equation. Okay, let's go to number 2. Y equals, what's the y-intercept? Y-intercept is also 1, but this time it has a positive slope, +1 slope, so there's our second equation. There's number 2. Okay, so again, if you just know where to look, these are not very difficult to construct. Let's go to number 3. So number 3, look at the y-intercept. It's -1. That slope is also -1, so I've got y equals -x minus 1. That is our equation for 3, okay, or the part of the line on 3. All right, and finally for number 4, what do we have? So y equals +1 slope, -1 intercept. So that is our equation. Okay, so looking at this, the key thing is we need some insight. We need to come up with the transformations ourselves. So look for some patterns. Well, to get us kind of started in thinking in this way, why don't we rewrite our equations a little bit? If I do, I can write the first one as x plus y equals 1. I can write the second one as y minus x equals 1. The third one as x plus y equals -1. And y minus x as -1. And then thinking of these, well, you see that we've got some common building blocks here. I've got x plus y, and those numbers go from -1 to 1. So I think a good idea would be, why don't we pick u to be x plus y? That means, and what would be the range of the values of u that would be sensible? I think from -1 to 1. Actually, let me make these transformations in green. Okay, what would be another choice? Well, I've got y minus x, and those go from -1 to 1. So that might be a great choice for our variable v. What does v go from? -1 to 1. Okay, a couple thoughts before we do anything else. Number one is we are coming up with our variables for u and v. So what if I decided to choose them in a different way? Well, that's okay. You would have a different transformation, and what's going to happen is the equations that you get change with them. Now, in this case, both the u and the v's go from -1 to 1. But, what if I did x minus y? Okay, so I could have done that for my v, and that's just going to change the direction, essentially, that I'm going through my transformation. Okay, cool. So what we're going to get then is basically the transformations in the u and v plane are the straightened out box, where in the uv plane, we're just going to say, okay, great, this is a rectangle. Oh, wow. Apologies, this doesn't look that great, but that's okay. And this is going to be our d star. Okay, now notice that what I've essentially constructed, just from the intuition, is we constructed t inverse, right? Where we know the curves in the D, in the blue xy plane, and we know how to send those to points in the UV. Okay, and I won't do this, but you should check yourself that those four corners get sent to these four corners with the transformations for U and V that I'm showing. Okay, let's check one of them. Okay, plug that in to the function for U. I've got U equals 1. And plug in for V, I've got 0 for Y and then -1. So I'm going to be here. Okay, so essentially you can see that if I go, well, I'm going to go around it in a certain order, and I don't really know the order I'm going to go just by looking at these pictures, right? So I've certainly come up with an order for D, 1, 2, 3, 4, but what tells us the order we're going to go in D star is actually the sign of the determinant. Okay, let's see. So let's not lose track of our goal here. So what is our goal? Our goal is to calculate this. So we're going to do that using the change of variables formula. What does that formula tell us? it tells us that the integral over d is the same as the integral over d star. Okay, I have to come up with some sort of function that's x squared minus y squared, but I need to rewrite this in the variables u and v. Okay, then I need to multiply this by the Jacobian of t, and then I've got du dv. Okay, so first, can we figure out what x squared minus y squared is in terms of the new coordinates? So think, I have to somehow get u and v into the picture. U is x plus y, v is y minus x. Okay, now this is where we got to be a little careful, because now you're thinking, let's factor. And factoring is fantastic, so there it is. And I hope you can catch, okay, when we start replacing pieces, you can see that x plus y is u, but x minus y is the other piece. I don't have that. I have y minus x, but that's okay. Just make the tiny adjustment where we're going to have a negative v. And what we've got then is that when we change our variables for x squared minus y squared, this just becomes a negative u times v. Great. Okay, so what we need now is to calculate the Jacobian. Okay, we need the Jacobian of t. Now, we didn't construct t directly. We have t inverse. So let's use our theorem where we do 1 over the Jacobian of t inverse. And now let's remember 1 divided by absolute value of the determinant of the matrix. Now, when we do it in terms of t inverse, the formula is we've got uv, x, y, sorry, x, y. Okay, and don't forget the reciprocal here. 1 over the absolute value of the determinant. Okay, I just like writing determinant. Okay, now what were our transformations? So there they are. The determinant of u in x is, sorry, not the determinant. The partial derivative of u in x is 1. Partial derivative of v in x is -1. Partial derivative of u in y is 1. Partial derivative of v in y is 1. Okay, so doing the determinant, I've got 1 plus 1 is 2. Okay, so my Jacobian of t is 1/2. Sweet. Okay, I've got the following integral to calculate. Double integral of negative u times v times 1/2, that's my Jacobian, times du dv. Now, why did I not fuss about the order? Well, look at the domain of integration in the uv plane. That just goes from -1 to 1, which was what we observed earlier, right? So u and v just goes from -1 to 1. Okay. So -1/2, pull that out front, do the sometimes useful trick, u du times -1 to 1 v dv. And looking at this, well, these are actually, again, think about u and v are just dummy variables. These are definite integrals where eventually I'm just plugging in numbers. So whatever we get, these are just going to be numbers. And because it's the same form of this integral, I just need to keep one of them. Okay, they're going to be the same answer, but of course I'll square it. All right, so negative 1/2. Let's go ahead and integrate this. I've got 1/2 u squared as u goes from -1 to 1. Okay, don't forget to square our final answer. Negative 1/2, and then I do 1/2 evaluated at 1 minus -1 squared. Okay, and what do I get? 1 minus 1, this is 0. So I end up just getting 0 everywhere, which is surprising a little bit. Like, did we do something wrong? Well, the calculation looks solid. So let's go back to kind of what we did over here. I did ask, is the answer surprising? Why or why not? Well, the insight is two things. Look at that function x squared minus y squared. The x squared and y squared are the same powers. And the idea is x and y has a line of symmetry like around here. So one way to think about it is that basically the shape that I'm integrating, this d, has the perfect amount where everything's balanced. So one way to think about it is these green zones, right, x and y's are both positive, and when I square them, basically it's got symmetry across this, right? So they'll cancel out. When they are both negative over here, I'm squaring them, so that doesn't matter. And again, I've got that as a line of symmetry. Here, there's parts where x's and y's are opposite signs, but because I'm squaring and these are perfectly symmetric across this line, everything is balancing out. So I think because this problem has this kind of symmetry built into it, the fact that we've got 0 is not really surprising. We could have probably anticipated that just by looking at the function we were integrating and then looking at the specific parallelogram, right? What I'm not saying is that if I integrate over any parallelogram, this would be 0, right? If our domain D was the parallelogram, I don't know, something over here, that doesn't really have y equals x symmetry, so I don't expect it to be 0 in that situation. Okay, cool. Great example. I think we're done. Okay, a new example here, example 9. So what would we like to do? So we're going to try to calculate the integral of x y squared dA over the domain D. Okay, so you can see the theme developing here, right? The function that we're integrating is not very difficult. So what makes it difficult is the domain of integration. So I've got the following curves, right? Xy equals 1, xy equals 4, xy squared equals 1, xy squared equals 4. So since these curves are a little bit trickier, I've actually provided a sketch of the curves here for us. So the blue ones below are, the lower one is xy equals 1, and the top one is xy equals 4, so these are hyperbolas. Okay, and the red curves are, the lower one is xy squared equals 1, and the top one is xy squared equals 4. Okay, again, since these are tougher to sketch, I've got a picture here, and when you actually look at this precisely, so if I've got a screenshot here of essentially what the zone looks like where they overlap. Let me grab maybe purple so that it stands out. No, maybe not purple. Green? Okay, so we essentially follow one curve from below, this other curve from above, okay, and then where it gets tricky is we switch to the blue curve. Again, it's kind of useless to draw over it, right? Where the blue curve kind of becomes our right zone, and then the red curve switches, okay? Let me just get rid of that so you can kind of see it with the colors, right? So here is the kind of like a cartoon version where I've exaggerated the curves a little bit so that you can kind of see um, how the curves look, right? We kind of start with the blue, then we switch to the, oops, we kind of follow the blue, then switch to the red for the left and the bottom curves, and then the top curves are, red, and then we switch to blue, kind of carving out this kind of weird shape um, that is a very distorted parallelogram. Again, I'm trying to make the parallelo curve a thing. Let me know if you like that. All right, well, we've got our change of variables for me here. Now what we need is we need to think, okay, well, what can we choose for our brand new variables? They don't tell them to us. So I think what is suggested here is, what are u comma v? I think since we've got x, y equals 1, maybe this suggests we can do u equals 1, u equals 4. And since we've got x, y squared equals 1, maybe we can choose that to be our v. And then we have v goes from 1 to 4. So I think a reasonable choice would be u equals xy and v equals xy squared. So in the language of this section, remember this is not t, but t inverse. Okay, so now that I've made those choices, let's make a copy and let's think about what we should have for a reasonable range of values. So let me just start off drawing a picture here. I think it's simple enough to say, okay, u goes from 1 to 4, and so does v. So this will be our d star. Okay, so what's next is, well, we look to the change of variables formula. How do I, well, actually, let's start with this. We've got, what is our goal? Our goal is to calculate the integral over d. D is the blue thing of x squared, xy squared, I'm sorry. Let me write dA generically as dx dy, but again, since I haven't described d as a type 1 or type 2 integral, we haven't quite specified this with enough information. Okay, so here we go. Change of variables formula says that this is going to be equal to a double integral over d star of x, y squared, but I have to change those into the u and v variables. And oh, we're in luck. X, y squared is v. So that is a very simple and clean change. Okay, next up we need to calculate the Jacobian of t. Actually, I'm going to do that right above this. So let me leave parentheses here for the whatever we get for the Jacobian of t. Okay, and then we have, of course, du dv. Since our region of integration d star is a rectangle, I don't really care about the order, but let me just put the u dv. Okay. So let's figure out the Jacobian of t. Okay, now we don't have t directly, so we can't calculate it, but of course, hopefully you're used to the theorem by now, the Jacobian of t inverse, and then we'll do the reciprocal. Okay, so this is a maybe brief way of writing it, but I don't like doing the -1 exponent because then I forget. I'll do it as the reciprocal of the Jacobian of t inverse, which means I've got to do the partial derivatives of u with respect to x and y, then the partial derivatives of v with respect to x and y. Give myself more room here. Okay, cool. Let's keep going. 1 over the determinant of, now let's build the matrix of partial derivatives. Okay, keep in mind I'm looking at u is going to be xy and v is xy squared. So the partial derivative of u in x is y. Partial derivative of u in y is x. Okay, looking at v next. Partial derivative of v with respect to x is going to be y squared. Partial derivative of v with respect to y is going to be 2x times y. Okay, so I've got 1 over the absolute value. Let's go ahead and calculate the determinant now. X pattern here. The product of the diagonals gives me 2xy squared minus xy squared. Okay, looking at this, I've got just 1 over, so 2 minus 1 is just 1, so I've got xy squared. All right, so that's great. That is the Jacobian of t. However, it's in the wrong variables. Right, I can't just put that right here because notice that I started setting up my integral in terms of u and v, and I need everything to be in terms of u and v, so what do? Panic. No, don't panic. All we have to do is just look at our transformation equations. Turns out xy squared is v, so huzzah! We've got a really simple formula for the Jacobian of t. Here it is, 1 over v. So give myself lots of space, didn't need it. And oh my gosh, look at this. v times 1 over v. Life is good. Life has never been this good. Look at the integral that we get. We get the integral of just 1 times du dv, and the limits of integration are just 1 to 4. And I don't even need to integrate. In fact, when you've got the function 1, this is really just the area of d star, which is just 3 times 3, which is 9. Okay, and the general theme here is, let's put a box over our answer. Notice, even though I'm using the area, I'm not going to put units squared here because, again, the original problem didn't start with the interpretation of the double integral as the area or as the volume of some object. So the answer is just 9, and great success. And this is kind of typical of how I'm going to test you on on this material, right? So I'm so sorry the videos are so long, but I love this section. I went thorough. I covered everything I wanted to cover. But if you kind of back away, and if there's one example for you to study for the test, it's probably example 9. Okay, and let me kind of summarize the themes here. The themes are either you'll have to come up with the sketches yourselves, or in an example like this, I will provide them for you if they're very complicated. Okay, you have to come up with the transformations for either t or t inverse. In this case, we looked at t inverse. Okay, but if you just know the statement of the change of variables theorem, if you kind of know the theory, the actual calculations are usually pretty straightforward. I mean, the partial derivatives were easy. The determinant was easy, and look at the integral, right? So when you change variables, everything worked out really nicely, and life is good. Okay, great. That's it for now. See ya.